Okay, so this is part two of the video presentation on confidence intervals. So in part one, we talked about the general form of a confidence interval, right? We say it's the estimate plus or minus the margin of error, right? And we say the margin of error, I'm going to put ME as margin of error, is typically the multiplier times the standard deviation of the estimate. Right, and so what we're going to talk about in this part of the video is talk about how we can actually derive the value of the multiplier that we want. We also went over some terminology, right, such as confidence levels and margin of error to kind of explain what those measures mean. But for this part, we'll focus on finding the multiplier of interest. So how do we find the z multiplier in our confidence interval for the mean? So a few things first, right? So a few things to remind ourselves. The formula writes the multiplier as this symbol over here, which this basically is the value of the z-score or the z distribution that corresponds, right, to the 1 minus alpha over 2 percentile. Right, so that's what this symbol represents. So what I'm going to do is to talk about why the formula for the confidence interval is the way it is. So let's work with this example over here, right? So we want a confidence interval, so we want a confidence interval at 1 minus alpha confidence. Right, so typically this is 0.95, so alpha is going to be 0.05. Now, we know the following facts. Fact 1, the sample means under some circumstances follow a normal distribution with mean mu, standard deviation given by sigma over square root of n. The other fact is that this implies that any normal distribution can be standardized. So if we consider the standard normal distribution, the standardized scores given by subtracting the mean and dividing by the standard deviation, which in this case is sigma over square root n, these z scores will follow a standard normal distribution, mean 0, standard deviation 1. Right, so we know these facts, and we're going to apply these facts to work through why the formula is the way it is. So pictorially, what we want with a 1 minus alpha times 100% confidence interval, right, and how it relates to this picture over here, the histogram or the probability density function of your standard normal is the following. So let's sketch the PDF of a standard normal, centered at 0. So basically what we want is the middle to contain the proportion 1 minus alpha. So if 1 minus alpha is 95%, then this center contains 95%. We know the entire area has to add up to 1, and the normal distribution is symmetric. So on these two tail ends, right, the two tail ends have to be alpha over 2, right, because these three areas have to add up to 1. So this value, right, on the x-axis represents the values of the standard normal distribution. So we want to find this value corresponds to the alpha over 2 percentile, right? Because alpha over 2 is to the left of this value over here. This value over here corresponds to the percentile of this plus that, right? So this is going to be 1 minus alpha over 2. If you add 1 minus alpha with alpha over 2, that's the percentile we get. Note, due to symmetry, these values have the same magnitude, i.e. to say negative of your z-score that corresponds to the alpha over 2 percentile will be equal to this value over here. Right, so there'll be the same value magnitude-wise. The one on the left-hand side is just negative, so this will be a negative value. That will be positive value, but they have the same magnitude. So we're going to use that fact. So how do we express all of these in mathematical symbols. So one could write the following: probability that your z distribution is between this percentile of the z-score and the right side, this percentile, z 1 minus alpha over 2, that's equal to 1 minus alpha. Right, so say probability that your z distribution is between these two values is equal to this shaded area. That's what this first statement is writing. So now we're going to play around with some of the other facts, right? So we know that, so this is the z distribution. We know the z distribution is equal to that. So I'm going to just sub this into that. So this implies that probability z alpha over 2 less than or equal to x bar minus mu over sigma over square root of n z 1 minus alpha over 2 equals 1 minus alpha. Right, so that's what we have. The next thing I'm going to do is I'm going to use this property to change this. Right, so this is basically telling me that this is the same as saying negative z of 1 minus alpha over 2. Right, so I'm going to do that, and I'm going to multiply the inequality right, there are three all these terms. I'm going to multiply every term by sigma over square root of n. So this implies probability of negative z 1 minus alpha over 2 times sigma over square root of n less than or equal to x bar minus mu times sigma over square root of n. This is equal to 1 minus alpha. The next thing I'm going to do is I'm going to subtract the sample mean from every side. So probability negative z 1 minus alpha over 2 times sigma over square root of n minus x bar less than or equal to negative mu z 1 minus alpha over 2 times sigma over square root of n minus x bar. That's equal to 1 minus alpha. Right, so the next thing I'm going to do then is to multiply all of these terms by negative 1 because I want to get rid of this negative sign. And if I multiply all the whole inequality by negative 1, the sign of the direction of the inequality changes. So this first term over here becomes now x bar plus z1 minus alpha over 2 times sigma over square root of n greater than or equal to mu greater than or equal to x bar minus z1 minus alpha over 2 sigma over square root of n. So that's your lower bound of your confidence interval, and that's your upper bound of your confidence interval. Right, so therefore my 1 minus alpha times 100% confidence interval is given by x bar plus or minus z 1 minus alpha over 2 sigma over square root of n. Right, because that's the lower bound and that's the upper bound, and it can be simplified into this form over here. Right, so that's kind of the derivation of the formula of why it exists the way it is. Right, it's based on the fact that your sample mean follow normal, can be approximated by a normal distribution, and so it can then be converted into a standard normal distribution, and we're using that fact to represent how we find this confidence interval, right? Why the formula is the way it is. So from a practical standpoint, you might say, well, how do we actually get the numerical value of this value on this z-score that corresponds to this percentile? So the way we do it in R is to use the function Q norm, and then we put in the percentile to find the z-score that's associated with that percentile. So if we are working with 95% confidence, then we type in Q norm 0.975, right? Because 1 minus alpha over 2 would then be 0.975, right? So we already explained why this is 1 minus alpha over 2. So you put in the percentile over here, and if you type it out, it will give you 1.96, right? And some books will say, oh, we can approximate this with 2. So just be aware, your confidence level if your confidence level is 0.95, you have to put in this value inside here, right? Because of the bell-shaped curve, right? Because it's 1 minus alpha in the middle, so it's alpha over 2 on this tail end. So this z-score has a percentile of 1 minus alpha plus alpha over 2, which if you work this out gives you 1 minus alpha over 2. So that's how we find it using R. In the previous set of slides, right, we used the function p-norm. So p-norm is kind of the other way around. You put in the z-score to get you the percentile. Right, so p-norm means you have the z-score, you want to find a percentile. Q-norm would be the other way around, where you know the percentile, you want to find the z multiplier, the z-score. Right, so they are basically inverse of each other. So these are just some exercises for you to try. I'm going to pause here a little bit to work out some of these z multipliers on your own, and then we'll go over the answers. Okay, so hopefully you pause the video and you try to work this out, some of these out on your own. So as a quick reminder, right, the code that we type into R is Q-norm 1 minus alpha over 2. Right, so in this case, alpha is 0.1, so we'll type in Q-norm 0.95. And you work that out, that's 1.645. At 98% confidence, your alpha is 0.02, so you will type in Q-norm 0.99, 2.326. And at 99% confidence, you'll type in Q-norm 0.995, and that will give you a multiplier of 2.576. So I kind of wrote over here, do you notice a trend in the z multiplier as confidence level increases? So you notice as confidence level increases, the z multiplier also increases, right? So you're more confident because if your multiplier is larger, then right, your margin of error will go up, right? Right, because your margin of error is multiplier times the standard deviation of the estimate. So you're more confident because your interval is wider, so you have more, right, more of your samples will have an interval that contains the true value of the population mean. So let's look back at equation number 2. Do you notice anything strange about this equation over here? So if you look at all of these, this sigma represents population variance. And the population variance is rarely known. So how can we actually apply this formula? So what can we do? And if you're thinking, well, could we use the sample variance in this place? You are actually on the right track. And so in part 3 of the slides, we'll talk about what changes when we use the sample variance. A lot of the ideas are still the same. There's just some minor differences that I will highlight.